Chapter 9, Number 41. An air-track cart with mass 20.25 kilograms and speed 1.2 meters per second approaches two other carts that are at rest and have masses of 2m and 3m as indicated in the figure. Carts have bumpers that make all collisions elastic. Find the final speed of each of the carts, assuming the air track extends indefinitely in either direction. And that's just so it doesn't fall off the track and do weird stuff. So this is really two different collisions. We have cart 1 hitting cart 2, and we know that what comes out of that at the end. So here's our original setup with 3, and then there's the first collision, and now cart 1 is going that way, and cart 2 is going this way, but cart 3 is at rest. And then there's another collision. Cart 1 has continued to move and is no longer interesting, and then cart 2 rebounds, and cart 3 flies off. And we're going to use the elastic collision equations that were derived in the chapter that I want to remind you're not responsible to memorize, but it's useful to know that they're there. And we're going to treat each collision separately. So I'm going to go back and redraw. So give us some space. And we're going to go back and say, so I have cart 1 coming in with V0, hitting cart 2 that's at rest, and then something happens, and then this becomes V1F, and this becomes V2F. And I'll have to be a little careful because as we go through this, we'll see that my V1F will come out with a negative, and I'll actually have to take the absolute value sign because I have already put the direction in here. All right, nominally, the way that formula is derived, we assumed that object 1 continued to the right, but in this situation, we know it comes to the left. So then we just go and we use the formulas from the book, and we find V1F is m minus 2m over m plus 2m times V0. So this is minus m over 3m V0, or minus 2/3, or minus 1/3 V0. So minus 1/3 of 1.2 meters per second, which is minus 0.4 meters per second. But we do want to be careful that actually our V1F is really plus 0.4 in the negative direction. And then V2F is going to be twice the original mass over the sum of masses times V0, and that's 2/3 V0, or 0.8 meters per second. And that heads to the right as expected. All right, for the second collision now, we have that cart 1 is moving this way at 0.4 meters per second, and cart 2 is headed this way at 0.8 meters per second, and cart 3 is at rest, and then collision occurs. Cart 1 continues to move off at 0.4 meters per second. Cart 2 rebounds, and I'm going to call this V2F star. And cart 3 flies off at V3F. And I'm doing the weird thing with the star here because I don't want to imply it's the same as the V2F earlier in the problem. So according to this, we have V2F star, as it were, is going to be the 2m minus 3m over 2m plus 3m times V initial star, if we want to call it that, which is what this will be, V initial star. And again, the idea is to just not have the same symbol mean different things. So this becomes minus 1/5 V0 star, or minus 0.16 meters per second. And again, remembering that actually in our actual final thing is really 0.16 meters per second because the minus sign is being caught up by that arrow. And then V3F is going to be twice the 2 mass over their sum times the new inbound speed, which is 4/5 V0 star, which is is 0.64 meters per second. So our final output is cart 1 moving leftward at 0.4 meters per second, cart 2 moving leftward at 0.16 meters per second, and cart 3 moving rightward at 0.64 meters per second. And we notice from these velocities they'll never collide again, which is good.